All right, we made it back here. We're going to start in section 8 of chapter 11. This is page 513. And what we're going to talk about essentially is phase diagrams. So we've talked about all the transitions between different phases, and it would be helpful if we put it all into one picture. And that's sort of what a phase diagram allows us to do. So they describe different states and the state changes that occur at various temperature and pressure conditions. Because remember, I told you, if you alter the pressure or you change the temperature, that's when you're making phase changes. So this diagram essentially is going to have pressure on the y-axis and temperature on the x-axis. And that will allow us to see if I increase or decrease the pressure, or if I change the temperature at a particular pressure, what state, what physical state, solid, liquid, gas, and so on, will my sample actually be in. Okay, so we're going to see all these lines on the graph and these different regions which represent that. And we'll also see a point called the triple point, which is where all three states, solid, liquid, and gas, exist simultaneously. And it's a really interesting spot, but it's a very difficult to kind of hit because you got to have a very specific temperature and pressure. Okay? So it's also interesting that for most substances, the freezing point increases as the pressure increases. And we'll see that as a common feature on many of these phase diagrams. So I want to start by showing you phase diagram here. Notice the temperature on the x-axis is increasing as you move to the right. So imagine we're talking about water, a substance we're really familiar with. As the temperature is increasing, it's going to be harder and harder to leave the gas phase, which makes sense. Okay, we see the liquid phase and the solid phase, and then there are these lines which represent boundaries between the different states, and that would be when phase changes happen. So I got some of them labeled here. The vapor pressure curve, if we go between vaporization and condensation, whether we're moving from the liquid to the gas or the gas to the liquid. And so this line would represent really that boiling point in essence, where the vapor pressure is equal to the external pressure. So notice when our external pressure is going up, our vapor pressure is also going up, and that's how we get to the boiling phase, or to the boiling point anyhow. Here's the fusion curve as we move between the solid and liquid phase, either melting or freezing, depending on which way we're going. And also we see the sublimation curve going directly from solid to gas or gas to solid. Remember, sublimation or deposition is kind of the same process. And then, of course, if we were to mark on this curve exactly where the critical point is, notice the line kind of ends there, and the boundary between liquid and gas just sort of becomes hard to determine. And so it would be a supercritical fluid. It's some of the properties of both. And so really this line color difference shouldn't remain the same. It should just get kind of blurry because you can't really tell what happens beyond that temperature very much. Or pressure, I mean. Beyond those critical points is what I'm saying. Okay, we also see the triple point. So if you happen to have that pressure and that exact temperature, you can reach the triple point where all three states kind of coalesce at once. And you could draw a line which corresponds to 1 atm, and that means you'll know that's kind of the curve that we live on. 1 atm is standard atmospheric pressure, so if you're in the lab working under regular atmospheric pressure, you live on this line. What you do is change the temperature instead of changing the pressure, and you know at a certain point water freezes, it gets really, it turns into the solid phase. And that's at a lower temperature, and as you raise the temperature, and you know the boiling point here at 1 atm is 100 degrees C if we're talking about water, and that's where it switches and all that business. So it's helpful to remember you live at 1 atm or 1 atm of pressure. You're kind of on this line, stuck on that line all the time, but there are all these other places you could be on the various pressure and temperature ranges. Okay, that's what the phase diagram helps us to sort out. So we can see and identify the normal boiling point very easily. And remember, we could find any other boiling point by moving the pressure, moving this line up and down. What would be the boiling point, for example, if you lower the pressure? Well, you just move this line down, and then you come over here and you find out where it crosses, and you know the new temperature at which it would boil if you adjusted the pressure. These diagrams are really great for that. Okay. So I went a little too fast there. So navigating within the phase diagram. It's not too hard to figure out, and this figure is given for you on page 514. And notice here, if you're starting at 1 atm, which is normal atmospheric pressure, and you're changing the temperature, notice the temperature here on the x-axis. As you increase the temperature, you're just moving along this line up and down. As you lower the temperature, as you raise the temperature, as you lower the temperature, as you raise the temperature, and so on. What state will your substance be at? So this is a phase diagram for a particular substance. I believe in this case it actually is the one for water. And so notice it's kind of odd because this line actually goes backwards, and that's a very rare thing that water does that other substances don't really do. Not very many others, maybe only one that I can think of. Anyhow, because it kind of moves backwards, that means that that's telling us something about this state here. Namely, if I decrease the pressure, I am increasing the melting point, which is kind of weird. Okay, I can also move up and down. If I lower the pressure, what happens? Well, eventually, if I stay at room temperature, say 25 degrees Celsius, and I just lower the pressure, eventually I'm going to make the switch between the liquid and the gas phase if I made it all the way down to here. So that means you can take regular room temperature and just lower the pressure, and you'll switch from the liquid to the gas phase. And that means if you go the opposite way, you can figure out what happens if you increase the temperature, or the pressure, excuse me. Although it's not that interesting for this diagram. All right, so we see the critical point. I mentioned that before. Here's the actual values for the case of water, the actual numbers that we're looking at here. The triple point occurs at 0.01 Celsius and 0.006 atm, so really low pressure, which is why it's difficult to reach. And like I said before, this curve here, the fusion curve, is backwards, kind of leans back, so to speak. In most substances, it goes forward. Well, water is a pretty unique substance. Okay, so here we are again, phase diagram for water, 760 torr. Notice as you increase the temperature from 0, which is right on the line of fusion, or melting, depending on how you want to think of freezing, basically, from solid to liquid, and then we keep moving, keep warming it up. Eventually we'll be able to get into the gas phase, and notice up here it's a supercritical fluid where you can't determine the difference. One of the interesting things about water is if we move to extremely high pressures, we can start to cause different solid phases or different crystalline phases. So remember, all those water molecules are locked into their crystalline nature, crystalline shape. But it turns out if you subject them to different pressures and temperatures, you can cause those water molecules to take on other shapes, which change the crystalline form of the water. And so an expanded phase diagram for water might look something like this. Notice we give these different phases of water kind of a different title. So we have ice 1, ice 2, ice 3, ice 5, 6, and so on. Notice ice 4 is missing. That's an interesting story there. Anyhow, under these particular pressure and temperature conditions, we can get water to switch into its different crystalline forms. And notice even here, the curve starts to bend back. So even though you're at a higher temperature under such high pressures, it still stays in the ice form or in the solid form. And it's important to note these are not to scale, because all of this stuff happens at a much, much, much higher pressure than 1 atm, which corresponds to where this line is, or the line that we normally live on, right? So, definitely not to scale. Actually, you should look this up on Wikipedia. It's pretty interesting. Spend some time looking over it. Now, we can make a phase diagram for anything. Here's a phase diagram for CO2, carbon dioxide, and notice the solid-liquid line kind of leans forward. That's the common thing you'll see for most substances. And we can find the triple point, the point at which the solid, liquid, and gas all exist at once, and that occurs under these conditions. And at 1 atm, notice we're in this sublimation region from solid directly to gas. So that's why we experience dry ice, like just going into the vapor phase and skipping liquid entirely altogether. And that happens at this temperature. And then it has a really interesting critical point, which is pretty easy to get to. I mean, 72.9 atm. It's hard to maybe generate on your own, but in the lab, it's not too bad. And so Carbon dioxide is often worked with as a supercritical fluid because it has some very interesting, fascinating properties that researchers in the field even now continue to work with and on to find new applications for CO2 as a supercritical fluid, and all the benefits that it has doing different scientific processes. Okay, so here's the one that your book has. Notice in this case we're living on the 1 atm line, and so we usually experience it solid to gas. This one's on page 515 if you're interested in looking at it in more detail. And also on page 515, this is figure 39. This is part B, the carbon dioxide part that we just looked at. And also we have this iodine part. Okay, so notice if you follow the line A, here you're just increasing the pressure. You can go from the gas to the liquid to the solid just by increasing the pressure without changing the temperature, if you're at the right temperature. Okay, and notice this line lies very far forward compared to water. There's the triple point. Notice it's at a reduced pressure and reduced temperature compared to 184 at least, but still above room temperature. So just because something freezes or changes phase, we always refer back to water because that's our common everyday experience. And so we tend to think, oh, something's freezing, it's got to be really cold. Well, these diagrams show that that's not true. You can freeze a substance at a high temperature. What substance are you talking about here? Okay, it really depends. And freezing doesn't have to happen when it's cold, and so on. All right, let's do some practice looking at these diagrams. Consider the phase diagram for CO2 shown. What phases are present at each of the following conditions, phase or phases? So at 20 degrees and 72.9 atm. So we would find 20 degrees on the curve, and we would go up to 72.9 atm. And notice we try to figure out what phase it would be in. 72.9 atm is up here, so it would clearly be in the liquid phase. So we're in this region that says liquid, and so we're in the liquid phase. What about at minus 56.7? So minus 56.7 is actually on this line, and 5.1 atm, that's right at the triple point. So what's the phase at that point? Solid, liquid, and gas. How about at 10 degrees C and 1 atm? Where's 10 degrees C? Somewhere in the middle here, and 1 atm means we're solidly in that gas phase. Minus 78.5 and 1 atm puts us right on the line here between the solid and the gas. So we're solid and gas if we're right on the line. What process is going from solid to gas? That'd be the process of sublimation. So you're right on the line there. And 50 degrees C and 80. So 50 would be above 30 over here, and 80 would be up here. So it would be a supercritical fluid at that point. Okay? We know that because we've passed the critical point in the temperature, and we've passed the critical point in the pressure. Okay, we've made it up to 80. So we could be past the critical temperature, like out here, but below the critical pressure and still be in the gas phase. Or we could be above the, below the critical temperature, but above the critical pressure and still be in the liquid phase. You have to cross both of these boundaries, both of the critical values here, to be a supercritical fluid. Okay, so imagine this line continues up and this line continues to the right, and so if you're kind of falling up in here, you're a supercritical fluid. That's sort of how you make the distinction, although to know for certain, you really probably would have to look up the exact values. Okay, there's all the answers we discussed. Okay, so phase diagrams are really useful for us for figuring out exactly what state, and these diagrams can be expanded like crazy. If you get to study physical chemistry, you'll probably look at them in a lot more detail between liquids and gases, and between mixtures of compounds. What phase exactly will it be in? And if you're making two solutions, will it be mostly one kind or the other? And what composition will the vapor actually be if you have a mixture of two liquids? Some really interesting stuff anyhow. And one of the key things that your book does discuss here is how water is an extremely extraordinary substance. This is section 9. And this is actually where we're going to end at for chapter 11, even though there is a section 10 about crystalline solids and crystal structure, and a section 11 here, and kind of a large portion of the chapter, even section 12. and 13, we're going to call it quits after section 9. So we're only going to go through section 9. 10, 11, 12, 13, and so on are important, especially if you study inorganic chemistry, okay? But they're a little bit beyond the scope of what we have time to talk about here. We need to move on. So let's just talk about section 9 here. Water, an extraordinary substance. This is page 516 and 517. Water has some very unique properties which allow life to be present here on Earth, and that's why when we go look at other planets, we're constantly trying to determine, is there liquid water, because it's that important to life existing. So most substances with similar molar masses are gases at room temperature, but water is a liquid at room temperature because it has such high intermolecular forces, the hydrogen bonding and so on. And that makes it unique. Water is an excellent solvent. It dissolves many substances, both ionic and polar substances. And remember, it has a large dipole moment. And other small nonpolar molecules even have some solubility in water. So it's really useful as a solvent, although it doesn't dissolve everything. It dissolves a lot of stuff that makes it really great as a medium, specifically in our bodies, which are made out of water, which is really important, so that way we can have all the transportation and all that kind of stuff that we need in order to stay healthy and living. Okay, water also has a very high specific heat for a molecular substance, which is interesting, which means that we can have a very temperate climate. Water has to absorb a lot of energy before it changes its temperature. So think about a place that doesn't have very much water in the atmosphere. Certainly here in Mississippi, it's humid all the time. We have a lot of water in the atmosphere, but think of like in a desert maybe. So that means if there's not a lot of water around to absorb the energy and kind of regulate the temperature, you're going to have times where it's really hot, and then at night it's going to get really cold because you don't have this layer of water in the atmosphere to sort of insulate and provide sort of a blanket, so to speak, for energy to maintain the climate. And so you can think about how we're able to have a very temperate atmosphere in most places on Earth because of the amount of water that's in the atmosphere and the high specific heat that it has. Another unique thing we already touched upon is that water expands when it freezes, even at pressures of 1 atm, about 9%. That means ice is less dense than water, therefore it will float on the liquid surface. Majority, almost all substances do not do that. The solid phase is more dense than the liquid phase, and when it turns into solid phase, it sinks to the bottom. Imagine if water, when it froze, the ice sunk to the bottom of the lake. How would that affect wildlife, marine life? Yeah, not a good way. So it's a very unique substance which allows life to be possible, which I'm very thankful for. Okay, that brings us to the end of section 9. And remember, like I said before, section 10, 11, 12, 13 talk about properties and structure of solids, which is a very interesting, fascinating study, but a little bit beyond what we want to discuss here at this point. So we're going to end chapter 11 right here. And we're going to move into chapter 12 next. Thanks for watching.